It is estimated that the universe contains up to 1 septillion stars. That's 1 followed by 24 zeros, with the Milky Way containing more than 100 billion itself. Stars begin as large clouds of gas and dust, called molecular clouds, ranging from 1,000 to 10 million times the mass of the Sun, spanning as much as hundreds of light years. Molecular clouds are cold, causing the gas to clump and create high-density pockets. And when these clumps collide with each other, they collect more matter, strengthening their gravitational force and increasing their mass. Gravity will eventually cause some of these clumps to collapse, and when this happens, friction will cause the material to heat up and lead to the development of a baby star called a protostar. Batches of newly formed stars are often called stellar cluster, and molecular clouds full of stellar clusters are known as stellar nurseries. Initially, most of the protostar's energy comes from heat released from its initial collapse. Immense pressures and temperatures in the star's core squeeze the nuclei of hydrogen atoms to form helium after millions of years, in a process called nuclear fusion. These nuclear fusion releases energy, heating the star and preventing it from further collapse under the force of gravity. Stars undergoing stable nuclear fusion are called main sequence stars, and this is the longest phase of a star's life, during which the luminosity, size and temperature will change over millions or billions of years. A star's fuel is provided by its gas, and its mass determines how rapidly it will run through its supply, with lower mass stars burning longer, dimmer, and cooler than very massive stars. Some low-mass stars will shine for trillions of years, longer than the universe has currently existed, but some massive stars will live for only a few million years. At the start of the end of a star's life, its core will run out of hydrogen to convert into helium, and the energy produced by fusion creates pressure inside the star that balances gravity's tendency to pull matter together, making the core start to collapse. This squeezing of the core increases the temperature and pressure, making the star slowly puff up. The details of the star's death depend very strongly on its mass. A low-mass star's atmosphere will continue to expand until it becomes a subgiant or giant star, while fusion converts helium into carbon in the core, which will be the fate of our Sun in several billion years. Some giants will become unstable and pulsate, periodically ejecting some of their atmospheres. Eventually, however, all the star's outer layers will blow away, creating an expanding cloud of gas and dust, known as a planetary nebula. All that will be left of the star is the core, called a white dwarf, and roughly the size of Earth. It will be a stellar cinder, gradually cooling over billions of years. A high-mass star will go further with fusion converting carbon into heavier elements like oxygen, neon, and magnesium, which will become fuel for the core. This chain continues until silicon fuses into iron for the largest stars. The energy produced from these processes keep the core from collapsing. However, each new fuel buy it less and less time, with the whole process taking just a few million years. And by the time silicon fuses into iron, the star runs out of fuel in a matter of days, as the next step would be fusing iron into some heavier element, but doing so would require energy instead of releasing it. The iron core of the star collapses until forces between the nuclei apply the brakes, at which point it rebounds, creating a shock wave that travels outward through the star. This results in a huge explosion called a supernova, while the core survives as an incredibly dense remnant, either a neutron star or a black hole. The material cast out into the cosmos by supernovae and other events enrich future molecular clouds and become part of the next generation of stars.